The primary problem is stability. Mathematical analyses suggest that such wormhole connections would be incredibly unstable, collapsing almost instantaneously under their own gravitational stress. Even if one could form, it would require exotic matter with negative energy density to hold it open, a form of matter that may not exist in nature. Furthermore, the violent conditions inside these structures would likely destroy any matter attempting to pass through, reducing it to elementary particles or raw energy. Another challenge facing white hole theory is the second law of thermodynamics. This fundamental principle states that entropy, or disorder, always increases over time in closed systems. Black holes fit beautifully into this framework. They have enormous entropy proportional to the surface area of their event horizons, and they increase the universe's total entropy by consuming ordered matter and energy. White holes, however, would appear to decrease entropy by spontaneously creating organized matter and structure from nothing, potentially violating this sacred thermodynamic law. Some researchers have attempted to reconcile white holes with thermodynamics by suggesting they could only exist in the very early universe, moments after the Big Bang, when the laws of physics operated under extreme conditions we don't fully understand. In this primordial environment, white holes might have briefly existed as temporary structures before decaying or transforming into more stable configurations. This leads us to one of the most intriguing proposals about white holes, the idea that our entire universe emerged from a white hole. Some cosmologists have suggested that the Big Bang itself might be understood as a white hole event, a singular moment when all the matter and energy in our universe was expelled from a cosmic white hole into the spacetime we inhabit. This interpretation offers a potential explanation for why the Big Bang appears to violate the normal rules about matter and energy not appearing from nothing. According to this white hole cosmology model, our universe would be the interior of a white hole, continuously expanding as matter and energy spread outward from the initial singularity. The cosmic microwave background radiation, that faint afterglow of the Big Bang that permeates all of space, would represent the last emissions from the white hole event horizon. While this idea is speculative and far from widely accepted, it demonstrates how white hole concepts might help address fundamental questions about cosmic origins. Let's examine whether white holes could exist as stable objects in our current universe. Most physicists believe they cannot, at least not for any significant duration. The problem relates to what happens at the event horizon boundary. For a white hole to persist, it must maintain a perfect barrier that prevents anything from crossing inward while allowing matter and energy to escape outward. However, quantum mechanics introduces fundamental uncertainties that would likely destabilize this boundary. Quantum fluctuations at the event horizon would create particle-antiparticle pairs, some of which might fall into the white hole despite the theoretical prohibition. Even a tiny amount of infalling matter would begin to disrupt the white hole structure. Over time, these quantum effects would accumulate, potentially causing the white hole to transform into something else, possibly a black hole, or simply to evaporate entirely through quantum processes. There's also the question of initial conditions. Black holes form through well-understood astrophysical processes, such as stellar collapse or the merger of dense objects. These formation mechanisms are grounded in physical processes we can observe and model. White holes, however, have no known formation mechanism. They would need to exist from the beginning, somehow built into the initial conditions of the universe. This requirement makes them extremely unlikely in our cosmos. Despite these challenges, some researchers continue to explore white hole possibilities. Carlo Rovelli and his collaborators have proposed that black holes might transform into white holes through quantum gravitational effects. In this model, when matter collapses to form a black hole, quantum mechanics prevents the formation of a true singularity. Instead, matter rebounds at incredibly high densities, creating a white hole explosion. This transition would occur on timescales that depend on the black hole's mass, with smaller black holes transitioning faster than larger ones. What if there were cosmic objects that expel everything instead of consuming it? Welcome to the mysterious world of white holes, the theoretical mirror twins of black holes that exist in Einstein's equations but have never been observed in our universe. Today, we're diving deep into one of the most fascinating and perplexing concepts in modern astrophysics. Imagine standing at the edge of reality, where the known laws of physics begin to bend and twist in ways that challenge everything we understand about space and time. Black holes, those cosmic vacuum cleaners that devour everything in their path, have captivated our imagination for decades. But hidden within the same mathematical framework that predicts black holes lies an even stranger possibility: white holes. Objects so bizarre that they violate our everyday understanding of cause and effect. To understand white holes, we must first revisit what makes black holes so special. When a massive star collapses under its own gravity, it creates a region of space-time so warped that nothing, not even light, can escape once it crosses the event horizon. This boundary represents a one-way door into oblivion. Everything falls in, nothing comes out. The mathematics describing this phenomenon comes from Einstein's general theory of relativity, specifically from Karl Schwarzschild's solution to Einstein's field equations, discovered just months after Einstein published his revolutionary theory in 1915. But here's where things get interesting. When physicists analyze these equations, they find something unexpected. The mathematics is time-symmetric. For every black hole solution that pulls matter inward, there exists a corresponding white hole solution that pushes matter outward. Think of it as playing a black hole movie in reverse. Instead of an event horizon that nothing can escape from, a white hole would have a boundary that nothing can enter. Matter and energy would spontaneously erupt from this cosmic fountain, expelled into the surrounding universe with no apparent source. The concept sounds like pure science fiction, but it emerges naturally from the same equations that successfully predict black holes, gravitational waves, and the bending of starlight. So why haven't we seen any white holes? This question sits at the heart of one of theoretical physics' most intriguing mysteries. Let's explore the theoretical properties of white holes in detail. A white hole would possess many characteristics opposite to those of a black hole. While a black hole's event horizon prevents anything from leaving, a white hole's event horizon would prevent anything from entering. You could orbit around a white hole, observe it from a distance, and even receive matter and radiation expelled from it, but you could never approach close enough to touch it or send anything across its boundary. The interior of a white hole would be even stranger. In a black hole, once you cross the event horizon, all paths through space-time lead inexorably toward the central singularity. In a white hole, all paths would lead away from the singularity and out through the event horizon. Time itself would flow differently. Inside a black hole, the singularity is in your future no matter what you do. Inside a white hole, the singularity would be in your past, a moment from which you emerged but can never return to. This temporal aspect reveals a profound problem with white holes. They appear to violate causality as we understand it. Matter erupting from a white hole would have no identifiable origin or cause. It would simply appear, fully formed, expelled into our universe, from a region that has no past connection to anything we can observe. This spontaneous creation of matter and energy seems to contradict the principle that every effect must have a cause, a cornerstone of scientific reasoning. Some physicists have proposed that white holes might represent the other end of black holes, connected by theoretical structures called Einstein-Rosen bridges, more commonly known as wormholes. In this scenario, matter falling into a black hole in one region of spacetime would be expelled from a white hole in another region, perhaps in a distant part of our universe, or even in another universe entirely. This idea has captured popular imagination and features prominently in science fiction, but it faces severe theoretical obstacles.